our guest, Jan Dul, who is a professor of technology and human factors. And there are some prior relations from the past in that field of ergonomics. But today, Jan, together with Cecilia, via different routes, we thought it would be interesting to invite Jan for a seminar, a workshop even, on necessary condition analysis. Jan has been, besides his many administrative positions in the school and his work in field of ergonomics, I think the last decade or so quite active in, let's say, rethinking methodology in the area of management research in different ways. What is the value of null hypothesis, significance testing, etc. But lately he's been very active in promoting and developing the use of necessary condition analysis. Okay? And the best person to tell you what that is Jan himself. So the floor is to you.
Yeah, maybe a little bit more about my background. Indeed, the last 10 years I was working on methodology, rethinking methodology, because I have a background originally in engineering. I'm a mechanical engineer, and from engineering I moved to medicine. I have a PhD in biomedical engineering, and after that I moved to the social sciences, because business administration and management is a social science. And what struck me is that in engineering we use research methodologies that are very different than in medicine. And in medicine they are very different than in the social sciences. And being a professor in the social sciences, managing social science as I said, I thought the social sciences can learn a lot from engineering and medicine in terms of research methodology. So that got my interest 10 years ago to rethink, as Finn said, all kinds of methodological traditions in the social sciences. And that was indeed about 10 years ago that I thought completely of a complete different approach to our logic and our data analysis. And that became to be necessary condition analysis. Yeah, you make this for me maybe. Sorry for that. So what I would like to do today is to explain what it is, but also to have a discussion with you, because this is relatively new. The first time that it was published in an official journal was in 2016, and since that time I have a lot of discussions all over the world about the methods, and I get a lot of feedback. So I hope also to get feedback from you, to learn from you, and maybe you learn from me as well. So, okay, some interaction. We have also kind of working, so that's why we have this grouping of the tables. You will be thinking also a little bit more in your own field about necessary conditions, and then we can have a nice discussion, I guess. Okay, let me start from where I come. I come from this world. This world from the natural sciences, where you want to predict an outcome. You have a nice function of x, and x are some variables that predict an outcome. So we have in the natural sciences beautiful formulas, beautiful predictions with two variables to predict an outcome. If you want to know the velocity, you just need a distance and a time. And even if you want to know the nuclear energy, you only have the mass and the velocity of the speed of light. So two variables in all these examples, and you perfectly explain an outcome. So that's what I started, mechanical engineering, in the engineering world. And then I moved to the social sciences. And they have the same formula, but there's one exception, there's the epsilon. Do you know that, epsilon?
It's a noise, maybe?
It is what?
A noise or something.
A kind of a noise. Basically, it is not a measurement error, but it is called an error. It's not an error. It is all other factors that predict y. So you have in social sciences a function. In natural science, 2 is enough, you don't have error. In the social sciences, we have all kinds of x's and an unknown term of everything else. And therefore, we have what we call the regression equations. All of you know, who knows regression equation, has heard about it? Yeah, okay. So, what we do in the social science, we say, okay, there's a constant plus a variable x that is multiplied by another constant plus the error term. So this is the most simple form of a prediction in the social sciences. One x and a lot of unknown things. And then we improve in the social sciences our prediction. We add another variable, adding. Or we added interaction term, multiplication. Or we added nonlinear term. And this is how the social sciences develop. We add, we add, we add in order to make a better prediction of the y. You already see that we have here two variables and all kinds of manipulations on these variables, multiplication, making it quadratic, etc. That's how currently the social sciences is everywhere. So the regression equation. Another example. It's not so interesting in the example itself. It's about a multinational company that has subsidiaries. And the question is, how does the subsidiary get attention from the headquarters? Apparently that's important. So how can you predict the attention that the subsidiary gets from all kinds of factors? The example is not so important, but just to show, what is the regression equation.
Plus epsilon.
Plus epsilon. So this is size of the company, autonomy of the company, the cultural distance, the network geographic distance, initiative taking, all kinds of factors that should predict the attention that you get. Plus epsilon. So how much does these 25 factors explain? Then we do the multiple regression analysis, and we look at the R square, we explain various, and we explain 27%. 25 factors explain 27%. And when I have seen these type of analysis over and over again in the social sciences, I thought, this is not the way to go forward. Because who is interested in this complexity in practice and still we're able to explain only 27%, which is a very common number in the social sciences. So we don't know a lot, actually. And that's because the phenomena are complex, but it's also because we exist as social sciences 100 years maybe, max. And in the engineering, it exists so much longer. Medicine exists so much longer. The funds for research are incomparable in the social sciences and the engineering and the medical sciences. So there's no one to blame for it, so to say, but this is the state of the art of the knowledge. And I think with this, you can't have evidence-based management, evidence-based decision-making, like we are looking for in engineering, like we are looking for in medicine. But in the social science, I think this state of the art tells us you have no message to practice. And that's not unique. So successful implementation of software, we probably have all experience if some system is implemented and it doesn't work as we want, right? So the success of it depends on 26 factors. The successful new product development depends on at least 20 determinants. Subjective well-being, look at that. So it is complex, so to say. And we are trying to approach to predict it with more and more, adding more variables, more quadratic parts, etc. And we continue and we add more and we add more and we can't explain. I think this will go on for the next 50 years like that. So this is my concern when I entered into the social sciences, and I was looking around for many years and I thought, this can't be true. Can predictions handle that many factors? No, they can't. Are they interested in models that explain only a small part of what you want to explain, no, they're not interested in these models. And this was my question. Can we find the real critical factors that we can tell to practitioners, this is something important for you. This you must do. And this is the basis of the necessary condition analysis.